All right, let's dive into black hole singularities.
Ah,
You sit over some fascinating research and
yes.
notes
Yeah.
on these points of infinite density, where
Right.
the laws of physics as we know them break down.
It's amazing, isn't it?
It is.
It really is.
So
Right.
someone like me
Yeah.
who hasn't spent my life studying astrophysics,
Right.
what is a singularity
Well,
and why should we care about them?
imagine taking all the matter in a star,
Okay.
maybe something many, many times larger than our sun,
Wow.
and compressing it down into
Okay.
a single point.
Hmm.
Now, that point, with its immense gravity, that's a singularity.
Hmm.
It's a place where our current understanding of physics just completely breaks down.
I could see how that would be a challenge.
It is.
I've heard that these singularities aren't just sitting there quietly.
No.
There's something about a Mixmaster universe
Right.
that sounds
Yeah.
more like a kitchen appliance.
Like a 1960s kitchen appliance. Yeah. You're not wrong about that.
Okay.
The term came about in the 1960s when physicists, Charles Misner,
Kip Thorne.
Thorne, Belinsky, Kolotnikov, and Lashitz,
Okay.
they were trying to model what happens near a singularity.
Okay.
Now, Einstein's equations of gravity
Right.
describe how space and time are warped by massive objects.
Right.
But they're so complex to solve.
Yeah.
So these physicists had to use simplified models
Okay.
and a lot of imagination.
I can imagine.
Yeah.
Their model painted a pretty wild picture.
Oh, yeah.
This Mixmaster universe wasn't exactly a calm,
No,
peaceful place.
not at all. It was,
What was it like?
they imagined space and time near the singularity,
Okay.
twisting, contorting
Yeah.
like a chaotic egg beater,
Really?
stretching and compression in every direction you can imagine.
Wow.
Now, they couldn't fully solve the equation,
Okay.
but this idea of a chaotic, dynamic singularity,
Yeah.
it stuck around.
So how did physicists go from this image of a chaotic egg beater
Right.
to
Yeah.
actually trying to make sense of what's happening inside a singularity?
Well, a key development came from the work of
Okay.
Belinsky, Kolotnikov, and Lifshitz,
Okay.
often called the BKL group.
Okay, the BKL group.
Yeah.
Okay.
They proposed this concept called decoupling.
Decoupling.
Imagine you're near a singularity.
Okay.
Gravity is unbelievably strong, right?
Yeah.
What they suggested was that different points in space
Okay.
become so distorted and separated by this intense gravity
Yeah.
that they essentially become isolated from each other.
Oh, wow.
A giant tangled knot
Okay.
where each strand starts moving independently.
So even within this
Right.
incredibly chaotic environment,
Yeah.
there might be a way to understand things piece by piece.
That's the idea.
Okay. But this was still all very theoretical, right?
Absolutely.
Okay.
But here's where it gets really exciting.
Okay.
While the BKL group couldn't fully prove their ideas in the 1960s, modern simulations and mathematical tools are starting to lend support to their predictions.
Really?
We're finding that this decoupling idea,
Yeah.
while incredibly strange,
Right.
it might be on the right track.
So we've gone from a chaotic egg beater
Yeah.
to this idea of decoupling.
Right.
But how does this all connect
Okay.
to the bigger picture of black holes,
Right.
singularities, and maybe even quantum gravity?
That's where we take another giant leap forward,
Okay.
both in time and in concept.
Oh.
In the late 1990s,
Okay.
a tool called the ADS-CFT correspondence
The ADS-CFT correspondence.
emerged.
Okay.
It's a mind-boggling concept
Okay.
that basically says you can translate problems between two seemingly very different descriptions of the universe.
Can you break that down for us?
Imagine you have two different maps
Okay.
of the same city.
Okay.
One map shows the streets and buildings,
Okay.
while the other shows the underground subway system. They look completely different, right?
Yeah.
But they both describe the same city,
Right.
just in different ways.
Okay.
The ADS-CFT correspondence is kind of like that.
So we can look at the map of the subway system
Yeah.
to understand something about the streets above.
Exactly.
Okay. How does that relate to black holes?
Well, on one side of this correspondence,
Yeah.
you have a higher dimensional space-time
Okay.
with gravity,
Okay.
what physicists call
Yeah.
anti-Sitter space,
Anti-Sitter space
or ADS.
or ADS-CFT. Okay.
And on the other side,
Okay.
you have a lower dimensional space-time
Okay.
without gravity.
I think I'm starting to see where this is going.
Yeah.
Could this ADS-CFT correspondence be the tool
Yeah,
that helps us understand what's happening inside a singularity?
exactly. Where
Okay.
gravity is extreme
Yeah.
and quantum effects are likely at play.
Okay.
That's the idea.
So,
And in 2019, physicist Sean Hartnell and his team,
okay.
they used this ADS-CFT correspondence to study theoretical black holes in this anti-de Sitter space.
Okay.
What they found is that even within this theoretical framework, the black hole singularity showed signs of chaos.
So even in this theoretical world,
Yes.
the singularity is still throwing a chaotic party.
It seems that way.
That's incredible.
It is.
Does that mean that this chaos
Yeah.
might be a fundamental property of black holes?
That's what's so exciting about this research.
Okay.
It suggests that this chaos might be inherent to the nature of black holes.
Right.
And understanding it could be crucial
Yeah.
to understanding how gravity behaves at the quantum level.
Right. I'm starting to get a sense of how complex
Oh, it's very complex.
and interconnected this all is.
It is, yeah.
We've gone from a chaotic egg beater
Right.
to decoupling.
Yeah.
And now this ADS-CFT correspondence.
This incredible tool
Yeah.
to study black holes.
Where do we go from here?
Well, the next step is to figure out
Okay.
what causes this chaos to arise.
Right.
Is it just a quirk of specific models?
Yeah.
Or is it truly woven into the fabric of gravity itself?
That sounds like we're about to enter a whole new level of complexity.
Oh, yeah. Wow. Okay. Definitely. To tackle those questions, physicists have been pushing the boundaries
Okay.
of theoretical models, trying to simplify things
Right.
down to their bare essentials
Okay.
to see if this chaos, if
Yeah.
it persists.
Okay.
And that's where the work of two physicists,
Okay.
Olling and Pedraza,
Olling and Pedraza. Okay.
it becomes really fascinating.
What did they do?
Well, they did something pretty radical. They took a theoretical model
Okay.
based on the ADS-CFT correspondence,
Right.
but instead of working with the full complexity
Yeah.
of Einstein's equations,
Right.
they made a bold simplification.
They simplified it.
They
They
did. They set the speed of light to zero.
Wait, zero.
Zero.
So nothing could move at all.
Well, in this theoretical model.
Okay.
Yeah.
But how does that help us understand something like a black hole?
It sounds counterintuitive,
It does.
but setting the speed of light to zero
Okay.
in these models
Yeah.
allows physicists to isolate
Okay.
specific aspects of gravity
Uh-huh.
without the added complexity of light's influence. It's
Yeah.
like trying to understand the flow of water in a river
Okay.
by first studying a still pond.
Okay, so by simplifying the model,
Yeah,
they were hoping to see if the chaos was still present,
exactly.
even without the usual rules of the universe.
Exactly.
Okay.
And what they found was remarkable.
What did they find?
Even in this simplified model, with the speed of light set to zero,
Uh-huh.
chaos still emerged near the singularity.
So even when you take away
Yeah.
one of the fundamental constants of the universe,
Right.
the singularity still wants to have a party.
It seems so.
Wow, what does that tell us?
Well, it's a strong indication
Okay.
that this chaos
Yeah.
might be deeply connected to the nature of gravity itself,
Okay.
even without
Yeah.
the complexities of the speed of light.
Right. But we're still in the realm
Right, we are.
of theoretical physics.
We are.
Okay.
Yeah.
So the next challenge is to see
Right.
if this chaos
Yeah.
can be connected to something we can actually observe in the universe.
That's the goal.
Okay, so this potential chaos
Right.
may be linked to gravity itself,
Yeah.
hiding within black holes.
Uh-huh.
But is it just pure randomness?
That's a great question.
Or could there be
Yeah.
some hidden order
Right.
within this chaotic mess?
That's a question that has puzzled physicists
Right.
for a long time.
Yeah.
And this is where the work of
Okay.
Sean Hartnell
Okay.
and his student Ming Yang
Right.
takes center stage.
Okay.
They decided to approach it.
Yeah.
This chaos from
Yeah.
a different angle.
Okay. How?
Well, instead of trying to track every single chaotic bounce and twist of space-time,
right.
they took a step back and asked, what happens if we average these bounces over time?
Right.
Could there be patterns
Yeah.
hidden within the seemingly random fluctuations?
So it's like looking for the signal
It is.
through the noise.
Yeah, that's a great analogy.
Yeah.
And what they discovered
Yeah.
was absolutely groundbreaking.
Okay, what?
They found that hidden within this chaotic averaging process
Right.
were specific patterns, and these patterns could be described
Okay.
using something called modular forms.
Modular forms, what are those?
Modular forms are
Okay.
definitely advanced math.
I was going to say, this is where I need a PhD.
But I can give you the gist.
Okay.
Imagine incredibly intricate
Okay.
and symmetrical patterns, like incredibly complex snowflakes.
Okay.
These patterns pop up
Okay.
in unexpected areas of mathematics,
Okay.
like number theory and string theory. What makes this discovery so exciting
Yeah.
is that these modular forms,
Right.
these beautiful mathematical structures,
Yeah.
seem to be connected to the chaotic heart of black holes.
Okay, so we've gone from a chaotic egg beater
We have.
to These intricate mathematical snowflakes.
Yeah, it's quite a journey.
It sounds like we're uncovering a hidden language.
It does.
Within the universe.
Seems that way.
A language that might help us understand some of the most extreme environments
Exactly.
imaginable.
That's exactly what's so captivating about this research.
Right.
By finding these mathematical patterns, these modular forms, within the chaos of a singularity, we might be able to bridge the gap between two of our most fundamental theories.
Okay.
General relativity, which describes gravity on a large scale, and quantum mechanics, which governs the world of the very small.
So these modular forms could be a key
They could be
to unlocking a theory of quantum gravity.
It's possible.
Something that has eluded physicists for decades.
It has.
But we can't actually observe this chaos directly, can we?
That's true.
Black holes are notoriously good at keeping their secrets.
They are,
Hidden.
Yeah.
Okay.
But that doesn't mean that we'll never find evidence for this chaos.
All right, how?
Well, as our technology and understanding improve, we might be able to indirectly
hear
the chaotic symphony.
But how is that possible?
Well, when black holes collide and merge, they send out gravitational waves, ripples in the fabric of space-time. These waves carry information about the objects that created them. And it's possible that subtle signatures of the chaos happening near the singularity might be encoded within these waves.
So by studying these gravitational waves, we might be able to pick out faint echoes.
It's possible.
This chaotic dance.
It's a challenge, but...
Yeah, but wouldn't these signals be incredibly faint and difficult to detect?
It's definitely a challenge. But our ability to detect and analyze gravitational waves is constantly improving with more sensitive instruments and advanced data analysis techniques. It's not impossible that we could one day tease out these subtle whispers of chaos.
Wow, this is incredible.
It is.
We've covered so much ground.
We have the early ideas of a chaotic
Mixmaster universe.
Mixmaster universe,
to this potential connection between black hole chaos and the quest for
quantum gravity.
Quantum gravity.
It's amazing.
It feels like we're on the verge of something truly groundbreaking.
It does, doesn't it?
It does. We started with this wild idea of a chaotic Mixmaster universe. Then explored how decoupling might help us understand what's happening near singularity. And now we're talking about
modular forms.
These intricate mathematical patterns.
These beautiful mathematical structures.
That could be the key to unifying gravity and quantum mechanics.
It's amazing.
It really is.
How far we've come.
It's a testament to human curiosity.
It is,
and ingenuity.
Absolutely.
We're using these tools, these mathematical frameworks, to probe the universe's deepest secrets.
The places we could never directly observe.
And even though we might not have all the answers yet, the fact that we're asking these questions and finding these connections is incredible.
It's mind-blowing, isn't it?
It really is.
It really is.
What we've learned about black hole singularities. Challenges.
It does.
Our assumptions about space, time, and gravity.
Absolutely.
So we've gone from 1960s kitchen appliances to these incredibly complex mathematical structures.
Quite a journey.
All to try to understand what's happening in this tiny region. What a wild ride.
It is a wild ride.
It really is.
It really is.
The journey is far from over.
No, it's not.
But it's clear that we're on the verge of some groundbreaking discoveries.
Absolutely.
As we develop more powerful telescopes, more sensitive gravitational wave detectors, and more sophisticated models. Who knows what other secrets the universe will reveal.
It's exciting to think about.
It is exciting.
Isn't it?
It is. Maybe within this chaos, within these seemingly random fluctuations, lies the key.
The key to the universe.
Maybe understanding how the universe works.
It's a beautiful thought.
It is a beautiful thought.
It is.
Perhaps one day we'll be able to listen to that symphony of gravitational waves and decipher those melodies of chaos.
From the heart of a black hole.
That would be remarkable.
It would.
It really would.
Really?
Well, based on what we've uncovered, I'd say the future of physics is looking pretty chaotic.
It is.
But in the most fascinating way.
In a good way.
A fascinating way.
Yes. Thank you so much for joining us.
It was my pleasure.
On this exploration of black hole singularity.
Absolutely.
Until next time, keep looking up.
Keep looking up.
Keep asking questions and never stop exploring.
Never stop exploring.
The wonders of the cosmos.
It's a wonderful universe out there.
It is.